Okay, so I've just produced an argument to suggest that this function, it's written right here, can be represented by this power series. But bear in mind that when I graph this function, notice this function is defined for, the domain for this function looks like it's everything except 1, right? Because of the absolute value, right?
But that could be 1 over there.
So what the graph I'm going to get right here won't look like the whole graph. It'll only look like this from -1 to 1.
Oh, okay.
The idea. It's not, so this power series is not going to produce the whole graph.
Yeah, it's only one.
Just a piece of it.
Okay.
Yeah. So we want to bear that in mind. And we know that among the series that converge, some converge fast, some converge slow. So it kind of depends on how quickly it converges. So let's see what the scenario is here. So this is my back to Desmos here. And I want to so let's start with the easy part. Let's say the function I'm thinking of is, so f of x, what am I doing? It's going to be negative natural log of the absolute value of 1 minus x, right? Why don't you like that? Maybe it wants parentheses. There it is. So that's what the graph looks like. Without the absolute value, it would just be, I guess, this much of it right here, right? Now, when I plug in this power series, depending on how many terms I include, it should start to look more and more like the graph, at least from -1 up to 1, right here. So there's this much of it, right? So we'll look at a few iterations of it. Let's just say, like, if I only kept the first term, x, right? Then I get a tangent line. That's actually a tangent line right there, right? And if I include 2 terms, that would be x plus 1/2 x squared. Right there. And you could think of this as being, instead of the tangent line, it's like a tangent parabola. Notice that close to that point, it looks a lot like that, right? In fact, it's kind of better than the tangent line, right? See how it follows the graph a lot closer than the line does, right? If I was to go a step further, that's y equals x plus 1/2 of x squared plus 1/3 of x cubed. And that's a cubic, right? And that's going to follow, looks like it follows the graph even better than the quadratic did. See how the black is kind of closer to it? Over here, it's starting to get kind of, let's just ignore that. So the purple, the actual graph is in green. Over here, it kind of diverges a little quicker, it seems, right? But still, I guess I would say the black line is closer to the green line than the purple one is.
Yeah, absolutely.
Yeah. Let's see if I can save some time here. Copy and paste plus 1/4 of x to the 4th. And we don't need to see that. So now what I have is a 4th degree polynomial, kind of parabola-like, right? But not. But you can see how it really follows the graph very closely, remarkably well, right? Yeah. And I would even dare say even a little bit better than the last one does. Add to that 1/5 x to the 5th, and let's see if it looks like the blue line is following better than the red line does. So the actual graph is in green. There it is. So blue does seem to follow it a little longer, a little closer. It eventually deviates away, though.
Right.
And I forgot to even look at what's happening from 0 to 1, right?
Yeah, that's even.
That's really good. Yeah. Really good. So yeah, so I think I think it's starting to become a little more convincing when you look at the graph. You know, plus.
What's crazy though
6.
is you add infinitely many terms, it'll never go
Mm-hmm.
like from 0 to 1.
Yeah.
If you add a gazillion
Mhm.
terms, it'll never pass the green line.
Mm-hmm. Mm-hmm. Yeah. Interesting. Yeah. So so by this time, it's really following it pretty close. I mean, if you were actually to plug in a number into this polynomial, like 1/2, and plug it into here, you know what I mean? I think it would be like, it wouldn't surprise me if it was accurate to like 5 or 6 decimal places. You know what I mean? Yeah. So indeed. So just looking at a few pictures doesn't prove anything, but it does make it persuasive somehow, even though it's not a proof. Yeah, it looks like, oh yeah, we can't see that. It looks to me like, based on this, that the negative natural log of 1 minus x is plausible. That this is the power series representation. Not to infinity, right? I also know that this is, it converges from -1 to 1. And that's kind of, you know, you can definitely see that happening right here. Once you get past -1, it just takes
It
off.
starts going to infinity.
Even if I take this series out to 100, you know what I mean? It's still gonna, like, once it passes -1, it's just gonna take off, you know? Yeah. And, what else? Yeah, and also you can also see it's not gonna, even though it's following a lot better over on this side, it's not gonna really, even if you took the series out to 100, it's not gonna work because technically the actual graph has an asymptote here. And even if you go out to the 100th power, it's gonna follow pretty closely, but it doesn't have an asymptote. It's still a polynomial. So the actual graph is gonna cross that asymptote, which the actual graph never does.
Right.
So, yeah. So this is just a fancy way of saying that it converges from -1 to 1. If you think about where it came from, which can't be seen on the screen, but the geometric series, it converges from -1 to 1. That's why this one converges from -1 to 1. But remember, we saw with the geometric series that does it converge at 1 or at -1? That would be a reasonable test question here. If you think about it.
At 1, no.
Certainly not, because that would just be 1 plus 1 plus 1 plus 1. And we had this discussion last time. What about at -1?
No, because just 1, 0, 1, 0.
Yeah,
0.
because it's a sequence of partial sums.
Right.
It doesn't converge. So yeah, so this is true. So this is the interval of convergence. Literally is from -1 to 1, and we have checked those endpoints, right? And this is also the interval of convergence here, but something interesting happens here. Notice that at the endpoints, right, I converge. Like, okay, if I plug in 1, does it converge?
No.
No, that's a harmonic series.
Right.
If I plug in -1,
I don't know. Does it?
if I plug in -1, that would be -1 plus 1/2 minus 1/3 plus 1/4.
Oh, yeah.
That's an alternating harmonic series, and that one does converge. So interesting, right?
Yeah.
So in this case, the actual interval of convergence is actually going from -1 to 1, including -1, but not including +1. But notice though, but nonetheless, so usually like, the interval of convergence, it kind of depends on the class you're in. In this class, well, in this class, a lot of times I'm interested in this one extra point where it converges, technically. However, notice it converges there conditionally.
Conditionally as
Conditional convergence. Right? Conditional convergence as opposed to absolute convergence. Right? Conditional convergence says that's when you have a series that converges, but if you remove all the negatives, now it diverges.
Oh, okay.
Right? Absolute convergence is a series that converges, and if you remove the negatives, it still converges. Right? Within this interval, it converges absolutely. But at -1, it converges conditionally. Right? So, yeah. A few things going on there. Okay, yeah. Also, too, interestingly, we can answer a question we couldn't answer before, right?
Which is?
So we saw in chapter 5 that if you have this series, alternating harmonic series, because it's an alternating harmonic series, we knew that this converges.
Right.
However, we didn't know what it converged to.
How can we answer that now?
Well,
By
if you
using-
plug in a -1 here everywhere, you get this series. So if I take this and just plug in a -1 here, 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 and here, I get -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus ... I think what we did last week, if I remember right, I think we stopped like here or here maybe.
Right.
And then we used like a remainder theorem for alternating series
Okay, so you're saying
to say how close it was. So that's what we did last week. But now with power series, I don't need the remainder. I know what it is.
by plugging in.
Yeah, because this, I just plugged in -1 everywhere, right?
Right.
I just plug in a -1 there.
So just negative natural log of 2.
Yeah.
Okay.
Yeah.
So this section is extra useful for when you have a series and you want to know
Mhm.
exactly what it converges to,
Mhm.
value is, if you can find the function.
Yeah.
How do you find the function?
I think that's probably the big deal today, is how to find the function.
Yeah, like as in you provide a series to us,
Mhm.
how would I know the function?
Yeah. 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 So yeah, we've managed to do a lot with the geometric series, and that's pretty nice. Make sure everything's centered, and we managed to do a lot with it. But I want to talk about. But there are functions we don't know how to deal with yet. You and Carter have mentioned them already, like sine, sich, and things like that. E to the x, for that matter. So for section 6.3, these are called Taylor and theories. Spell that right? Laurin. Laurin. Did you say RIN? Yeah. Taylor and Maclaurin series. So these are just special types of power series. They literally are just power series, actually. So, I guess we could have just called them power series, but I guess you got to give credit where credit's due.
The extra hard ones, that's what they did.
Yeah. So suppose you have a function that, suppose you have a function, an arbitrary function, and you want to find the power series.
Right.
Right? We've seen examples of this, of particular functions, and we figured out some clever ways to come up with power series. But what if you don't have any clever ways? Then, for a given function, if I know this is a power series centered at 0 here, right?
Right.
Or perhaps a power series centered at
A.
You know? If I remember right, I believe in this next section we're going to call the power series centered at A will be called a Taylor series. And if it's centered at 0, a Maclaurin series. You know? Yeah, that's right. So yeah. So a Maclaurin series is a power series. Centered at 0. And a Taylor series is merely a power series centered at A. Okay, no big deal. We're just giving things names.
Right.
Things we've already dealt with and have been working with. All right? But what we've been, and what we've been doing is we've been trying to figure out what these coefficients are. Right? And so what we're going to be able to do is kind of give you a systematic way just to be able to find the coefficients in general. So let's see here. So for example, let's just start with the Maclaurin series. It's relatively simpler than a Taylor series, only that is centered at 0. And let's pick an actual function, right? Something easy to work with. Something that's easy. Part of what we were doing is
Y equals X.
yeah. Okay, yeah.
That's the
Okay, yeah, that would be
not a power series.
technically it is.
Yeah.
It would be a power series if f of x equals x. That would be a power series where a sub 0 is, or no, a sub 0 or a sub 1. I guess, actually, you know what? I should be starting at
start at 0, right?
so that I have a constant term. Right? Let me quick edit. This would be a power series with a sub 0 equal to 0, a sub 1 equal to 1, a sub 2 equal to 0, a sub 3 equal to 0, a sub 4 equal to 0.
Wait. I'm not tracking why because
Because this is 0 plus 1 times x plus 0 times x squared plus 0 times x cubed.
Yeah, you're right.
Yeah. So yeah, some power series are easy. Anytime the function is a polynomial, then the power series is self-evident, right? That's probably a good thing to mention. I wasn't planning on it, but that's yes, that ought to be recognized. That would be like a test question I could ask that would probably mess everybody up.
Yeah.
And then you realize afterwards it's like there wasn't really much to it.
Yeah.
So something other than a polynomial, right? And so something other than a geometric series. All right. How about?
So some kind of rational function, right? Well,
Yeah, we could.
But then,
How about,
wouldn't you just find a way to make it a geometric series?
It turns out that there's other functions that you might consider more complicated, that are actually easier. Like,
Yeah, at first glance, I'd be like, that's probably gonna be complicated.
yeah. But actually, it turns out this is like probably the easiest one.
Please, enlighten me.
So, I'm gonna, instead of using sigma notation, I think it'll be a little more enlightening if I just write it in an expanded form. So I don't know the coefficients, so I don't know what to put. So I'm just gonna put A0 plus A1x plus A2x squared plus A3x cubed, and so on and so forth. Who knows where it converges? Or even if it, who knows even if such coefficients exist? Well, if the coefficients exist, then I should be able to plug in numbers for x, right? That would make the left-hand side equal to the right-hand side.
Right.
So for example, if x equals something easy like
1 or 0.
0 is even easier, right?
Yeah.
If x equals 0, then the left-hand side becomes e to the 0,
Well, yeah.
which
1.
is
1.
1. And on the right-hand side, a0 is just 0. I mean, sorry, a0 is just what it is what it is. I don't know what a1 is either, but because it's multiplied by 0,
Yeah. 0.
then it's got to be 0. And the same can be said for every single other term.
So then,
Hey,
1.
I just deduced that a0 must be 1. If a power series exists, then a0 must be 1.
Wait a second, if a power series exists,
Mm-hmm.
then a sub 0 is 1.
Yep. We'll mark that as important. But that's one down, infinitely many more to go. So I'm hoping to observe a pattern along the way, so that I'll have to literally go through every single one.
Okay.
So yeah, let's see here. How do I figure out the other ones? Well, we saw that it's if a power series exists, if there's a region where it converges absolutely, then you can take the derivative. That means the derivative of e to the x should be the same as the derivative of all these.
Yeah, the derivative of e to the x is e to the x.
Yeah, that's why this is the easiest one to work with. E to the x is e to the x. But the derivative of a naught, which I now know is 1,
0.
would be 0. The next term would be,
I don't know.
well, this is a constant times x. So,
Oh.
so whatever it is,
Yeah, so a sub 1.
it's going to end up being a1, right? The next term, if you take the derivative,
Is 2 a sub 2.
yeah,
And then
times x. And then what?
3 a sub 3 x squared.
Yeah.
No, wait,
So yeah, sometimes you might have to write out a lot of terms to really see the pattern, right? So yeah, let's see here. Maybe I'll go ahead and show one more. I know that the next term would have been a4x to the 4th. So 4a4x cubed. And that's kind of slick because it gives me access to the next coefficient. I'm really going to get a lot of mileage out of this trick. If x equals 0,
And
that
they all-
tells me that e to the 0
is 1.
is a1
And then a sub
plus
0, 0, 0. So equal a sub 1 has to equal 1 also.
Nice. Oh, why did I switch to blue? Oh, I want this to look good now, in case other people look at it. So yeah.
What is the, oh yeah, my bad, Professor, just real quick, what is your thing called? If I
What thing?
YouTube it?
Oh, just Jason Engel.
Alright.
That's my channel. Yeah. I'm putting in these tags for calculus, sequence, series, things like that. Ratio test, it would hopefully get you to it. But I don't know, there's probably more popular channels that would come up first. Oh, and all the links are on Canvas.
Where?
Under the announcements.
Oh, okay.
Yeah. I think I have room to do one more computation, right? So now that I know, the first two coefficients. They're both a. They're both one.
One.
Right. So I'd like to know what is a2. All right.
So take the derivative again.
We're going to be taking a lot of derivatives in this.
That's why it's just one.
Yeah.
It's just over and over.
Exactly. So if there was a more complicated function, these derivatives could get out of hand pretty quickly. So yeah, so I should be looking at the derivative, because I'm taking the derivative of the derivative. A1 disappears because it's a constant, right? It wasn't before, but now it is.
Right.
So I end up with a 0 plus what?
So take the derivative of 2a sub 2 x.
Yeah.
So 2a sub 2 is a constant though, right?
Yep.
So it'd just be 2a sub 2.
Exactly. And without an x. Plus?
Oh, I'm confused. What, is that 2a sub n?
Oh yeah, my bad.
Okay. And then you just take the derivative of that. So 6a sub 3
Mm-hmm.
x.
And you know what I'm going to do? We all know that 3 times 2 is 6, but I'm going to leave it like this.
Just to see the pattern.
It'll make it easier to see the pattern, yeah. A3 times what?
X.
Just x. Plus
4
4
times 3.
times 3 times A4.
X squared.
See why you need to show a lot of terms? Because we keep losing terms as we go. So, but now the plot thickens. We use our usual trick. Plug in 0. As we saw twice already, e to the 0 is 1. But in this case, the only term that doesn't disappear
2a
is
sub 2.
2a sub 2. All the rest is 0. So what did that tell me about a sub 2?
So if it's 0, then 2a sub 2 equals 1.
Mm-hmm.
So 8 sub 2 is 1/2.
Yep. That's why I said the plot thickens is something other than 1. Yeah, and we could keep doing this all day long. We're doing pretty good. We got 3 of the coefficients, still infinitely many to go, but I want to go far enough so it's clear what the pattern is, right? So you really just keep going, right? The third derivative would be e to the x as well, but the power series looks different, right? Well, it looks different. It should be the same power series, actually.
Yeah, so 3 times 2a sub 3 is the first term, yep.
Right.
X, yeah.
Plus?
4 times 3 times 2,
Uh-huh.
and a sub 4 x.
Right. If I had to guess what the next term was, even though I haven't shown it over there. Seems like.
Well, I know you're bringing the cube down.
Yeah.
3, 2, 4, 3, 5, 4.
Yeah. That makes sense, because to begin with, it would have been a fifth degree term, right? So the 5 would have come from the first derivative, the 4 would have come from the second derivative, the 3 would have come from the next one.
Derivative,
Yeah. A5 times x squared, or something like that. x5, 4, 3,
see
No,
there.
I don't think there's supposed to be a 2, right?
Yeah, okay. Yeah, that's right. I'm getting ahead of myself. Dot, dot, dot. Yeah. And that could be verified by just simply, you almost, if you're kind of new to this, you might want to just go all the way out to like the 10th.
10.
You know what I
Yeah.
mean?
Yeah.
It takes a lot of paper, but you have a little more elbow room.
Understand,
Yeah. So now I can see that if x equals 0, then just like before, 3 times 2, a3 plus 0, and everything else is 0.
So a sub 3 equals 1/6.
Mm-hmm. Yeah.
Still not seeing a pattern here.
Yep. So, but yeah, I mean.
So the next one would be 1/4 times 3 times 2?
Mm-hmm.
1/24? Is that not right? I'm just guessing patterns now.
I was expecting this, but that doesn't come until the next step. 2 comes from here. Yeah. Yeah, so we can see then that.
Oh, so it is 1/24, yeah.
Mm-hmm. Yeah. Yeah, plus 0, so a4 is 1/4, 3, 2. Let's see here. How about what if I said this? You wouldn't really use the power rule in this case, but I suppose you could. It's 1
2
times x to the 0 power.
Wait, say again? It's 1 time.
You notice that, like, you're not really thinking the power rule here, but x is the same thing as x to the first power.
Oh, yeah, you're saying, bring it down to the, okay.
Yeah. So, that gives some justification for what I want to write that'll make the pattern a little more, jump out at you a little more. This is 3 times 2 times 1.
Yeah, and then it's like factorial.
Yeah.
On the bottom, yeah.
In fact, this 1/2, I could have said it's 1/2 times 1.
Yeah.
So it's really just 2 factorial.
Yeah.
And so this is another case where, technically I ought to really prove it, but and the proof he would use is a technique of proof that, called induction. You see a pattern that's happening.
The opposite of deduction.
Yeah. Well, you figure it's like it's a technique you would use when it's like it's pretty clear what the pattern is, and you just want to prove that it actually does keep going forever.
Mm-hmm.
And but in this class, at this stage, I think we're all pretty well convinced.
Yeah.
But yeah, if we had more time, it would be kind of fun to study that technique and apply it here. But I'll venture a conjecture. I think it appears to me that the nth coefficient is going to be 1 over. Well,
The n factorial, right?
yeah. See how the subscript is the same as the
4.
largest number? So n factorial. And that being the case, right, I can now say that e to the x equals 1 plus 1 times x. I'm looking at all these things I have boxed.
Oh.
Because these are the coefficients.
Coefficients to
that go
term.
here, here, and
Yeah.
here.
Okay.
So I'm looking, so as I write what I'm writing, I'm looking over here and peeking at all these little boxes so I know what to plug in.
Okay.
That's 1 plus 1 times x, or I'll just write x. Right? The next one's going to be 1/2. So plus 1 over 2x plus
1 over
Mhm.
1/6.
Yeah.
1/6.
And I'm just gonna write 3 factorial and 2 factorial. Right? Plus, oh, sorry, x
squared, right?
Okay.
One, actually no, this one should have been a square actually.
Oh yeah. Cube.
See that? And that's, I mentioned like either earlier this week or last week that there'll be some power series that are worth memorizing. And that's one of them. And I don't think it's that bad. It's not that hard if you just think about the pattern. This is another example that you could pop into Desmos. Maybe just pick a point to stop at and see if the graph looks like an exponential function, right? Another question I'd want to ask is, you know, the one that we looked at a moment ago, it didn't converge everywhere, just from -1 to 1.
Right.
I wonder where this one converges. Will it look like the exponential function just from -1 to 1? I know it's centered at 0.
All right.
If the radius of the convergence was like 5, then maybe it looks like the graph from -5 to 5. You know, who knows? So yeah,
Are you really saying you don't know? You just wondering, or you?
No, I know.
Oh, okay.
Yeah, yeah. It turns out that, and so kind of like how I was advising you to memorize the geometric series along with the interval of convergence. You know what I mean?
Okay.
Remember that 1 plus x squared is 1 over 1 minus x, but memorize that coupled with the fact that absolute value of x is less than 1, right? For that same reason, I'd like you to know this, but I'd also like you to know where it's valid. For what values of x is this true? Right? So let me write
Well,
down.
definitely 0.
Yeah.
So.
For what values of x does sigma, I'll write down the same thing in sigma notation. Sigma 1 over n factorial x to the n from 0 to infinity converge. This is a compact way of just saying whatever, the same thing as what I wrote here. And that's a question that you already know how to answer, right? You're going to use the ratio test,
Okay.
right?
Yeah.
According to the
limit,
so
limit is n approach 0 of the absolute value of. Man, that's a lot of stuff.
Yeah.
1 over n plus 1 factorial.
it all ties together, huh?
Yeah.
That's the limit. I'll just, since all our limits in this class are as n goes to infinity, so I'll just write limit, it's enough.
Okay.
Absolute value a n plus 1 over
a, so then.
and so in this case, that's including the x, so that's going to be the limit of the absolute value of
X
1
over
over
n plus
n plus 1
Oh.
factorial times x to the n plus 1 all over
1 over n factorial.
x to the n. And that is the same thing as the limit of, now these are always positive anyway. It can be simplified to be n factorial over n plus 1 factorial. Is that okay? Times the absolute value of n. I showed these steps in a lot more detail a bit earlier in the example problem, but you see what I did is this is a fraction, I can flip it and multiply it by the top, so this n factorial ends up on the top.
Yeah.
You end up with x to the n plus 1 over x to the n. There's one more x on the top than there is on the bottom, so it simplifies to that.
But wouldn't that just be 1 over n plus 1?
As n gets huge, yeah, you're right. as n gets huge, that ends up being 1 over n plus 1 without a factorial.
Yeah.
Times the absolute value of x. And we want to ask for which values of x is this limit less than 1, right?
Wait, so which values of x is the limit less than 1?
Yeah. So for example, if x equals 1/2, and you take the limit as n goes to infinity, what do you get?
1/2 of really tiny number.
Yeah.
Yeah.
Which would be tiny.
A tinier number.
So the limit would be 0.
Yeah.
So yeah, so that by the ratio test it converges when x equals 1/2. What if x equals
So
2?
all numbers, right?
Yeah.
All real numbers. Yeah.
So no matter what x is, just think of x as a constant.
Yeah.
As n gets huge, even if x was huge,
Still
it'll eventually get small.
yeah.
That limit is 0, and 0 is less than 1. And that's for all x. So that means that the radius of convergence is infinity, the interval of convergence is all real numbers.
Okay.
So yeah.
Wait. The radius is infinity. You said the radius is
Yeah.
infinity, and the interval is
Yeah.
all real numbers, right?
So yeah, so just like the geometric series, you want to know this pattern, but you want to know where it works. And so I'll extend this green box and just say
Everywhere.
for all x. So yeah, so something more powerful is happening than in the picture we drew before on Desmos. Like on Desmos, the
Yeah.
other function
So
only
this-
converged narrowly.
So that'll look exactly the same.
Yeah, everywhere.
Really?
If you go out to infinity,
Right.
right? It will be kind of a similar picture in that it starts, the more terms you add, it kind of follows the graph a little closer and closer.
Right.
But even if I stop at 100, there's going to be a point beyond which it's going to start to really go away from the
Slip,
graph.
yeah.
But you just keep going, right? So that's a nice one.
That's pretty.
Yeah. And the other ones that I'd like to do is like sine and cosine. Why? Because the derivatives are easy,
Oh,
right?
yeah.
The derivatives are easy. And so,
So pretty much when you do the derivative, take the derivative and start plugging in zeros so you can
Mhm.
solve for that.
yeah. So yeah, the only the only ones I really want you to memorize would be the geometric series, e to the x, sine x, and cosine x.
Okay.
Right.
Write that down.
Yeah. I'll be writing it down eventually too. So I would go through a similar process as what I just done. Is that good grammar? I don't know. Go through a similar process as what I just done.
Doesn't matter. This is more important than grammar.
You know, I could do the same thing with what I just did to e to the x, I could do that to sine, right? It'd be slightly more complicated because the root of sine is not sine, but cosine. And the root of cosine is negative sine.
Negative.
So yeah,
Switching.
that sort of thing is going to be happening. It would be good practice. But what I'm going to do, also in the interest of time, is this. Is I'm going to try and develop a formula that I could use to just, to do this a little quicker. So in other words, I'm not going to commit to a particular function. I'm just going to say f of x
So, just like help me out for my notes. What I'm finding the formula to find the coefficients in the power series.
Yeah, so given a function, can I find the coefficients, right?
Of the power series.
Yeah, yeah. And it depends on the function. The function not all functions have a power series, right?
Right.
So, but the conditions under which the function is going to have a power series, it's going to be with
I'm going to say that all the derivatives exist. So, with all derivatives
As in, like you'll never get to a derivative that's just a constant and then
Yeah.
zero.
Yeah, so things like e to the x, all the derivatives of e to the x
Keep
exist.
going.
All the derivatives of sine exist. All the
All
derivatives of
exist.
cosine exist. So those are pretty nice. Do all the derivatives of a polynomial exist?
No, eventually it'll get to just constants, right?
Eventually you get to a constant and then to zero.
Zero.
And then from that point forward, it's always going to be zero. But those are functions.
Oh, okay. So trick question.
Trick question.
Yeah.
So yeah, so even with polynomials, all the derivatives technically exist.
Okay.
It's just that most of them are zero functions. Right. So yeah. So and you can see why I need all the derivatives to exist, because if I'm going to do what I just erased,
Yeah.
I needed to look at lots of derivatives of e to the x, right?
Well, then what? I'm sorry. Just side note. What's the case where a derivative would not exist?
Absolute value function,
Oh, okay.
right? Yeah. Because it's continuous at the corner, but it's not differentiated there. So there's no power series for that one. Yeah. All right, so supposing the derivatives exist, I can see that, for example, if I plug 0 into this function, then I plug in 0 into the function, right? And I plug 0 into the power series, and it's a little harder to see in this form, but notice, because you might be tempted to say it's equal to 0.
Equal to 1.
Yeah, it's equal to
It would be 1.
a 0 plus 0 plus 0 plus 0 plus 0,
Okay, yeah.
right? Because the first coefficient, I don't know that it's 1. In the last example, it was 1.
It was 1 in the last one.
But in this case, if I was expanding this out, what you would see is a0 plus a1x plus a2x squared, and so on and so forth. When you plug in 0, anything with an x attached to it would become a 0. But there is one term among these that doesn't have an x attached to it, and that's when you have an x to the 0 power, right? So I think so. It's safe to say that if you're trying to find a power series for an arbitrary function, you can safely say that the first coefficient is always going to be, at least for a Taylor series, it's always going to be the function evaluated at 0.
But then it would, for the Maclaurin, it would just be evaluated at A, right?
Exactly. Not that different. If we understand this, then the Maclaurin will be a cinch. So similarly, just like we did before, the derivative. I'm kind of stretching you a little, I think it was a lot clearer when I wrote it out in
Right,
expanded
yeah.
form. But I want you to see how to do this in sigma notation too.
Would be A sub 1 x, right?
It would be, so the general formula is going to be the coefficient times the exponent.
So A sub n plus 1? Or no, A sub 1?
Well, remember when you had a sub 2x squared,
Yeah.
it became 2a sub 2 x.
In the derivative, yeah, okay. In the derivative, yeah.
So I'm going to write it like that. So term for term, I'm just doing the same thing over and over again.
Like a derivative,
Yeah.
right, and down.
But a subtle detail that's often missed in sigma notation is that one of those terms was a constant term, right? One of
Yeah.
those terms was a constant term. That means it was supposed to become 0. And it doesn't need to be included in the sum anymore, right? So what I'm about to write is a mistake, so I'm going to erase it after I write it. It would be a mistake to write
it would be n starting at,
Yeah.
okay. Starting at a, well, how would you write?
Well, another way to see it as a mistake is that if you try to plug it in, 0 minus 1 is negative 1.
Yeah.
You know what I mean? So yeah, so the first term, we can omit the first term and just start at the next term, which is when
0 plus 1?
when n equals 1. Just say n equals 1.
Yeah.
Out to infinity, right?
I was saying 0 plus 1, so see your pattern?
Oh yeah, that's good. That's good. That's good. So using that same trick as usual, I can now see that in general, if I plug in 0 into the derivative of the function that I have in mind, we're going to apply this to sine and cosine in a few moments.
So if you plug in 0, then it's just n times 3,
Mhm.
so n, right?
So every term except for 1 has an x attached to it. Every term that has an x attached to it in the expanded form
Becomes 0.
becomes 0. So which one doesn't have an x attached to it? The first one. When n
Okay.
equals 1, this is x to the 0 power. When x equals 2 or anything bigger than 2,
It'll have a value.
yeah. So the only non-zero term is going to be when n equals 1. And when n equals 1, it's 1 multiplied by a1. In conclusion, a1 is f prime of 0. So I think it's safe to say, that whatever function you're thinking of, if it has a power series, the first term is just that function evaluated at 0, and the second term is just going to be that function whose the derivative of that function evaluated at 0, and that's the number that goes in front of the x.
So for that sine and cosine would always just be
Yeah.
1, 0, 1, 0, and 1, 0, right?
Sort of. You'll see. You'll see. Sort of. Yeah. I see what you're saying. Yeah, 1, 0. Oh yeah, 1, 0, 1, 0.
Yeah.
Sort of. Remember the derivative of cosine isn't sine though.
The derivative of cosine is negative.
Yeah.
Sine. Oh, so negative
1, 0, negative
Negative
1, 0,
yeah.
1, 0, negative 1,
And
0.
like a
Right.
triangle.
So hopefully this trick is starting to get.
But an
familiar.
alternating cosine sine.
Yeah.
That'd be just 1s and 0s, right?
So the sine and cosine will be alternating. Right? To take the second derivative is just the derivative of the first derivative. So and the general rule is, remember, it's kind of a little challenging to see what's going on, but remember, n is a constant. A sub n is a constant. So this exponent is also a constant. The only thing that's a variable is the base. So what would the next formula be?
It wouldn't be like the derivative, like, so n minus 1.
Mm-hmm.
Wait, am I taking the derivative with n in front? So like n squared minus n?
Yeah, this is just a coefficient.
That is just the coefficient? Yes.
This is just a coefficient times x to some power.
To n minus 1, right?
So the power rule says you bring down the n minus 1
Yeah, and multiply
and
by.
then decrease it by 1. And that n minus 1 is going to become part of the coefficient.
Yeah, so I wouldn't say n squared minus n.
Yeah, I'm going to leave it.
Just
in
leave it in
standard form.
parentheses.
Yeah, like that.
Okay.
See? But now the exponent has gotten 1 smaller.
N minus 2.
Yep. And
That's right.
since the first of these terms was a constant term, I'm going to start now at 2. A lot of subtle details when you're doing it with segmentization. And so now looks to me like if I plug in 0,
That's a sub 2.
what I get, most of the terms are going to end up being 0. The only thing that doesn't become 0 is the one that doesn't have an x attached to it. The one that doesn't have an x attached to it is the one where the exponent is 0. That is to say, when n equals 2.
A sub 2.
And when that happens, you end up with 2 times 1 times a 2. In other words,
Oh, because you're plugging it in the end. Okay, sure.
right? I'll do one more step just to make the pattern clear. I think it'll jump out at us a little quicker after having looked at the last example more thoroughly. So taking the derivative term for term, right?
3.
It's a pretty complicated looking coefficient, but we're going to take this
Times
exponent.
n minus 2.
Mhm.
A sub n x to the n minus 3.
Mhm.
And then the denominator is factorial here too, isn't it?
Yep.
Of
So the,
whatever
fact,
the
so
power
the fact that we
is.
got a factorial last time really had nothing to do with it, the fact that it was e to the x.
Right.
You know what I mean?
I thought it was.
Factorials are very common for
Series.
series, yeah. You know, for this reason. And where is this going to begin?
3.
Yeah. So now it's plain to see that all but one of these terms has a x attached to it. So if I plug in a 0, I can now see that the third derivative of the function evaluated at 0 would be
The derivative might be 0 over 3 factorial.
Yep. So a sub 3 at this point, I think I'm ready to venture a guess. It looks to me like the nth term.
Sorry, I'm trying to write this. What's up? The nth term
Yeah, the nth coefficient of the power series.
is
right?
the nth derivative evaluated as 0.
Yep. Yeah, and you know, I don't know if you've seen this notation before. Like, if usually I use these primes,
Yeah.
but if you can't write them all out, you can put it in parentheses like this. That means the nth derivative. Oops, not evaluated x though.
Evaluated as 0
Yep.
over n factorial.
Yep.
That's crazy.
Yep.
Should have just learned this first. That
I
seems
know, huh?
easier than all the other stuff.
Yeah, the point of the other exercises is just to kind of get familiar with
Understand.
the properties of it. So now that we're familiar with the properties, we can just jump straight into that and start doing some crazy stuff with it. Right?
Oh yeah, I'm sure there's gonna be hard ones, but
Yeah. So this is the point I wanted to get to, right? You can see why I needed that condition that all the derivatives exist, so that all the coefficients exist. And now I can kind of say something a bit more.
So then, oh, my bad, Professor, quick question. So say we have a series that's not starting at, like a series that started at 5,
Mm-hmm.
we could find out the previous term by integrating.
If a series that started at 5, find the previous term.
Like if we had a series
Uh-huh.
and we had all these terms,
Yeah, yeah.
if you were like, what's the term that was before this?
Mhm.
We could just use this, but like integrate, like integrate, right?
What's the term that's before this?
Does that make sense what I'm saying?
I see what you're saying. Instead of derivatives, integrate?
Yeah,
Define the previous
define
yeah.
previous term.
Yeah, as long as you know what the function is.
Right.
Yeah, you might be able to pull that off. Yeah. Seems believable. But in general, you might recall from, if you think about 151, differential calculus, integral calculus,
in general, I'd say it's easier to take the derivative than it is to find the
Oh
antiderivative.
yeah, absolutely.
You know? Yeah, but yeah, that's an interesting idea to kind of pursue and explore, see if it yields anything useful. But yeah, in light of the result I just given, you know, that seems to be true. You need induction to prove it.
That seems to be true. Yeah.
Good enough for us, though.
Nah, yeah, you told me it's true. It's true.
Yeah. So now I have a formula for the coefficient. It is the nth derivative evaluated at 0 over n factorial times x. You'll have to do some further investigation to see where it converges. So no wonder the power series for e to the x is what it is. Because every derivative of e to the x evaluated at 0 is 1. Right? But take something slightly more complicated like sine x. And I find a power series for that.
Excuse me.
Do it like that. I'd like to find a power series for sine x. What should can I find a formula for the coefficients, basically? Well, with this formula in mind, I'm interested in finding all the derivatives of sine of x. And then once I have all the derivatives of sine of x, I'd like to know what they are at 0. Right?
Divided by n factorial.
Yeah, yeah. So let's see. Well, let's see. If f of x equals sine x, then f of 0 equals
Wait, what? 1. Wait, f of oh, okay, 0.
Yep.
Yeah. My bad.
f prime of x would be,
Cosine, and that equals 1.
so f prime at 0 would be 1. F double prime at x would be,
Negative sine.
so f double prime at 0 would be
0.
f triple prime.
Negative cosine.
Mm-hmm.
That's negative 1.
Nice. The fourth derivative
Sine?
yeah, the negatives cancel, right? And I think at this point I can kind of think, well,
Just
it kind of gets back to where I started, so the same thing's going to happen again. And so if I want to evaluate this, I think I can see that this is just going to be what it was before. And the fifth derivative, evaluated at 0, is just going to be what this was. And sixth derivative, evaluated at 0, is just going to be the same as what that was. So I think we've gone far enough. So let's see here. If ever you're kind of starting to get kind of confusing, starts to get kind of hairy, you can at least ratchet down the difficulty by just writing it in expanded form, right?
Yeah.
I think that helps. So let me try that here.
Yeah, let's do that.
The first term is a sub 0, right? Also known as the 0th derivative evaluated at 0.
That's 0.
And that's a 0. So I'll put a 0 here. And the next term is something times x, right?
Yeah. So it's 1.
Yeah, so I'm looking at the
Or the
first
coefficient
derivative.
is 1, right?
First derivative evaluated at 0 is 1, divided by 1 factorial. So it's going to be 1. I'll just put a 1. The
So
next
1x.
Mm-hmm.
So the next one is 0 over 3 factorial. Or no, wait, 2 factorial.
Yeah. So if there's a 0 there, it's pretty simple, you know. 0 x squared, I'll say. What comes next?
And then 1 over
Mm-hmm.
3 so 1/6
Mhm.
x cubed.
But bear in mind, this is a negative 1 now,
Okay.
right?
Yeah.
So I should
minus, yeah.
I really should be putting a minus 1 over
3 factorial
3 factorial
x cubed.
x cubed. Yeah, maybe I should leave this as, I'll just write 1 factorial. Maybe it'll make the pattern jump out at me more easily. And
0x to the 4th.
yep. And then
1 over 5 factorial x to the 5th.
yeah, it's positive, right? So plus 1 over 5 factorial x to the 5th. Wow. And I think the next one's gonna have a 0. The next one after that's gonna be a minus, right?
7 factorial.
Yeah. So yeah, that's so yeah, so now how do I say it, right? I have the series, I have an idea.
Yeah.
I think I can even like keep going without having to look at this anymore. You know?
Right. How do you say it?
Yeah. Well, it's worth noting that for every term that has an even power on the x, there's a 0.
Mm-hmm.
For every term that has an odd power on the x,
It's alternating though.
but it's alternating. Yeah. So we're gonna have a negative 1 to the
Negative
end.
1 to the end. Yeah, I know that much.
Yeah, that much is clear. But yeah, so what we're gonna do is this. In light of the fact that a lot of these terms have a 0 in front of it, I'm not even gonna attempt to include it in that pattern. I'm just gonna jump past them, right? So what I'm gonna do instead is I'm gonna write it like this. Let me just, I'm gonna put a K here. The book I haven't checked, the book probably uses an N, but I'm just putting a K here to emphasize that I'm not really hitting all the indices. I'm just gonna hit the odd ones, right? But I'm only gonna do the odd powers, right? Things like 2k plus 1. Right? That's how you generate odd numbers, right? Multiply by 2, so it's going by 2's. Put the plus 1 so that it's starting at 1. So if k equals 0, I get 1. If k equals 1, I get 3. If k equals 2, I get 5.
Yeah, but then when you put in, yeah.
Well, like you said, it's clearly alternating.
Yeah.
I'm either going to put a k or a k plus 1, whatever makes the
Oh,
sign
yeah.
right.
K. I said and that meant K.
I think k will do it because when k equals 0, negative 1 to the 0 power, we're gonna say is 1. And the first term, when you have that x to the first power, that one should be positive, right?
Yeah.
So when k equals 1, that is to say when I get the x cubed,
3. Yeah, it's negative.
it's going to be negative. That's just the way I want it to. In every single one of the non-zero terms, there's a fraction with a 1 on top. But what goes on the bottom? It's not going to be k factorial because it's not
Yeah.
1, 2, 3, 4.
So it's 2k plus 1 factor, or k plus 1 factorial?
No, you're right. I mean, it's worth noting that what you're taking the factorial of is always the same.
That's the, yeah, 2k plus 1 factorial.
So that helps. That observation helps a lot.
This is intense.
Yeah. So there you have it. sine of x, he does have a power series, and that's it. In expanded form, it would look like this.
So that, my bad.
Mm-hmm.
So if I seen a problem like this, the series from a number to a finite number,
Mm-hmm.
would that be the same number except just decimal estimations? If I just plug the same number into sine, right?
Mm-hmm. If you plug the number into sine.
Yeah, like if this was just from 0 to 5.
Right.
And all those terms, if I plug in x equals 5, it would be the same as if I just plug sine 5.
It would be pretty close.
Yeah, just
Yeah.
decimals off.
Yeah, it kind of depends how far away from the center. So the further away you get from the center of convergence, the less accurate it'll be.
Oh, okay.
Yeah.
Right, because it only looks.
But yeah, we have a remainder theorem for power series too.
Right.
So
just do that.
In fact, actually, it's called Taylor's theorem.
Oh,
Taylor's theorem literally gives you a bound on the remainder.
Okay.
So yeah, that would be interesting. You know, plug 5 into sine, and only going up to this point, and how close is it? You know. Yeah, and also too, like e to the x, I'd like to know where does this converge. You know. You'll be using the ratio test here as well. But the nice thing is that because of that factorial, you know, something similar is going to happen, and we're going to say for all x. Turns out it converges for all x. For cosine, you're going to go through a similar process, right? The pattern will be pretty similar to what's right here.
Except the negatives and the positives are a spot over, right?
It's going to have, yeah, and so for this reason, we're going to be hitting, instead of the odd powers, it's going to be the even powers. And you're going to end up with a pattern that looks like this.
K plus 1. Or
I'm going to start at 0. I'm going to put a negative 1 to the k.
it would be negative
1 over 2k factorial.
Take
It's
away
going to
that
be even.
plus 1.
And x to the 2k. And that's also.
For all x. That's crazy.
Yeah. I'll leave it for you as an exercise to confirm that that's
Hey,
true.
you're telling the truth.
Yeah, and those are the big four, right? You now have officially been shown the big four. E to the x, the geometric series, sine x, cosine x. But yeah, in the exercises in the homework, you might be doing that with other things too.
These are the ones you're talking about, memorize those?
Yeah.
Those four. Sorry.
Mm-hmm. Yep.
Memorize them as in being able to, as soon as I see it,
Mm-hmm.
that's one of these.
Yeah. But even if you forgot, I mean, you would go through a process like this.
It takes forever.
Yeah. And you know, the process is sped up a bit if you have that formula at least. You know.
Just take bits for Carter.
How we doing? So yeah, I guess that's about it
Yeah.
for today.